Alright, so our topic now is linear independence of vectors. Alright, so these are vectors here. These three vectors here are in R3, right? So in column vector form, this is a vector in R3 because it has three components over here, x, y, and z, right? Okay, and I have three of these vectors, right? Now, what you want to notice about these three vectors, right, is that this third vector you can actually get as a sum of the other two, right? So if I add first vector and I add the second vector, I'm going to get a third vector over here, right? All right, so roughly speaking, what that means is that this vector over here actually depends on these two, right? There's an interdependence among the vectors, right? Where one of the vectors you can get from the other two, right? And by get from the other two, I mean you can take multiples of the other vectors, add them together, right? And then you'd get the vector that you want, right? Okay, so this vector 1, 1, 0 I get as a sum of these two, right? So this 1, 1, 0 vector depends, if you want, on these two, right? Now, right, this is good. You see in that the 1, 1, 0 it depends on these two. It's a sum of these two, right? But that isn't really how we want to phrase it here, right? And later on, for the purposes of definition and calculation, this isn't probably the best way to phrase it, right? And usually for us, the best way to phrase things is when you have a zero on your right hand side over here, right? So what I do is for this equation, I just rearrange it a little bit, and I take this vector here and move it across on my left hand side, right? And when I move it across on the left hand side, I introduce a minus sign, right? You could formalize all of these things by additive inverse, right? But this is just like if you're doing any sort of like basic algebra, when you move something across today, from the right hand side to the left hand side, you would introduce a negative sign in front of it. Alright, anyway, so this equation here, this vector equation, I can rearrange in this form, right? Okay, and and it's saying the same thing basically, right? So if I take this first vector and multiply it by 1, in other words, I get the 1, 0, 0. Take the second vector here and multiply it by 1, I'll get 0, 1, 0. And then when I add it to the negative of this vector here, right, I'm going to get 0, right? And you can check, right? If you look in the first component, you have a 1 here, you're going to have a 0 here, and you're going to have a minus 1 there. So 1 plus minus 1 is going to give you 0, right? Second component, you'll have a 0 here, you'll have a 1 here, and then you have a minus 1 here. You get a 0, and then in the third component, you just add in zeros to get 0, right? So this left-hand side, and we saw this notation already, right? This left-hand side is a linear combination of these three vectors over here, right? Okay, and we saw examples of that, right? If I have, say, three vectors over here and I multiply them, each of them by scalars, like this over here, multiply each vector by a scalar and then add it up, that is what's called a linear combination, right? So what I have is on this left hand side over here, this is a linear combination of these three vectors, and I'm looking for a specific linear combination. I'm looking for a specific linear combination that will actually give me 0 over here, right? Alright, so this sort of linear combination is what's referred to as, well, the sort of equation over here, right? This is referred to as a linear relationship among your vectors here, right? Okay, so what's the definition of linear relationship? Right, if I have a vector space, so in this case the vector space that I'm looking at is R3. I have a set of vectors, right, u1 to un, right? So in this case I have three vectors, u1, u2, and u3, right? And if I have an equation of this form, right? So what you're doing is you're taking your first vector, multiplying it by a scalar, such as this over here, right? So you take your first vector, multiply by a scalar. Take your second vector, multiply by a scalar. Third vector, multiply by a scalar, right? Okay, so if I have an equation where I have scalar times first vector, scalar times second vector, scalar times third vector is equal to the 0 vector, right? then that's called a linear relationship, right? Okay, so this here this is a linear relationship here, right? Where the C1 is equal to 1, the C2 is equal to 1, and the C3 is equal to minus 1, right? Right. Right. Okay, so this is a linear relationship here, right? It's a non-trivial linear relationship. By non-trivial, I mean that I it's not just zeros. These scalars here are not just zeros, right? So one thing you want to notice is that if I have this vector equation over here, instead of using 1, 1, and minus 1, right? If I really wanted to get 0 on this right-hand side, I could just use 0 here. I could use 0 here, and I could use 0 here, right? And if I use 0 here, 0 here, and 0 here, right? What I'd get is 0 times this vector, which just give me the 0 vector. Likewise, I'd get the 0 vector over here, and I get the 0 vector over here, right? So if I had 0 here, 0 here, and 0 here, that would be a trivial linear relationship, right? So that's what this is saying over here, right? If I have a linear relationship like this, right? And it turns out that these constants, the scalars over here, C1, C2, Cn are just 0, right? Then that is in fact a trivial linear relationship, right? And we'll see an example of this in a while, right? Right. Okay, so once I have for over here for these vectors, if I have a non-trivial linear relationship, in other words, these scalars aren't zero, right? Aren't all zero, right? And I still get the 0 on the right hand side, right? Then this is a non-trivial linear relationship. And once you have a non-trivial linear relationship, what that means is that by definition the vectors are going to be linearly dependent, right? So the vectors are, if you want, they're dependent on each other, right? And this is intuitively, as I said, right? These three vectors aren't independent of each other. This third one you can get as the sum of these two, right? Alright, so I'll define this a little more precisely, but for the time being, you want to read it as this, right? Once you have your vectors here, and you could set up this sort of vector equation where you have, so you can set up a vector equation such as this one over here, right? With scalars in front over here where your scalars aren't necessarily all equal to 0, right? Once you could set up a linear relationship like this, right? Then what that means is that the vectors are going to be linearly dependent, right? Okay, so let's look at this second example here, right? I have three vectors, and each vector is in three-dimensional space. It's an R3, right? All right. Now, in this case over here, right, I could write this third vector as a sum of these two, right? And that is what this second equation does for me, right? But it turns out that you won't be able to do that in this case, right? If, for example, you try to write, you wouldn't be able to write this last vector as a sum of these two, right? Because if you notice in your third component over here, you have 0 here and 0 here, right? So no matter what you do, right? Even if you multiply this by a scalar and you multiply this by a scalar, right? If you take some linear combination of the first two vectors, you'd always have 0 in your third component, right? So there's no way it will give you this 1 down there, right? So you'll never be able to write this third vector as a sum, as a linear combination of these two over here, right? And likewise, you can actually argue that, for example, this first one over here, you'd never be able to write it as a sum of these two, as a linear combination of these two, right? Okay, so this situation over here is different from this situation that we had, this first example that we had, right? This first example, we could write one of the vectors in terms of the other two, right? As a linear combination of the other two, right? But we can't do that in this case, right? Okay, and I'm saying it's not possible to do it, right? Now, how would you show that it's not possible to do it, right? How you'd actually show that, and this in fact is the definition that we'd use to check for linear independence or dependence, right? Is how you do it is you examine this vector equation here, right? You examine this vector equation, right? And when you work out this vector equation and you expand it out, right? You multiply C1 inside and you form a system of equations. What's going to happen when you solve is you'll see that the C3 has to be equal to 0, right? And you could sort of see it over here, right? If you multiply throughout over here, your component, third component here would be 0, the third component here would be 0, and this you'd get a C3 is equal to 0, right? So that will give you a C3 is equal to 0. And if you look at from your second equation, what you're going to get is C2 plus C3 is equal to 0. And because the C3 is equal to 0, that gives you the C2 is equal to 0. And if you consider your first component over here, the equation that you would get is C1 plus C2 plus C3 is equal to 0. And now that you know that C2 and C3 is 0, that tells you that C1 is 0, right? Okay, so I didn't write it out over there. What you're doing is you're really just forming a system of equations, right? We do that later on, right? But for the time being, so we do it over here. I'll do an example of it, right? But for the time being, to show, I'm saying that you can't write one of these vectors in terms of the other two, right? And how you actually show that formally is you check this vector equation, right? And when you solve this vector equation, if the only solution that you get is C1 and C2 and C3, the scalars out in front there are just all 0, right? Then that means that the only solution for this vector equation is this one over here, right? Okay, so for these three vectors, the scalars that you have to choose in front of them, right, so that when you form this linear combination, they all have to be 0, right? And well, that's always the case, right? If you have a vector here and you multiply by 0, you'll get a 0 vector, right? This vector here and you multiply by a 0, you get a 0 vector. And likewise here, you get a 0 vector. If you add 3 0 vectors, you're going to get a 0 vector, right? So this one, when you have zeros over here, this equation would always hold, right? So what I'm saying here is that if you consider this, right? Consider this vector equation. If the only possible solution is when you have 0 here, 0 here, and 0 here, so the only possible solution for C1, C2, and C3 is the 0 here, the 0 here, and the 0 here, right? What that means is that these vectors, you have no relationship among them, right? And you call this linearly independent, right? Okay, so these vectors here, these are linearly independent vectors, right? You cannot express one as a linear combination of the others, right? And how you show that formally is by considering this vector equation. Or more specifically, what you do is you check this implication over here, right? So you check this vector equation here, right? You work it out, and if when you work it out, the solutions have to be all 0, the C1, C2, and C3 all have to be 0, right? Then what that means is that these vectors are linearly independent. All right. All right, so our last example here, right? And this example, we will look at a little more detail in the notes, is this one here, right? So again, I have three vectors in three-dimensional space, right? And I'm saying that these vectors are dependent, right? Right, you can get one from the others, right? As a linear combination of the others, right? But how you check for the dependence, or how we want to state it in this class, right, is by looking for a linear relationship like this, right? And if you have a linear relationship where some of the scalars here aren't all 0, right? So in this case here, the scalars had to all be 0 in order for you to get the 0 on the right hand side, right? In this case, for this example over here, that's not true, right? These don't all have to be 0 to get the right hand side is equal to 0. You can find non-zero ones over here, right? And the non-zero ones, a non-zero one would be if you have a 1 over here and you have a -2 over here and a 1 over here, then you'd get 0 vector here, right? And you can check, right? When you multiply this out, you'll have a 1 over here, you have a -4 over here, plus a 3, that would give you 0, right? And here I'd have 7 here, plus 7 over here, -14, so I get 0 here. And same thing over here, right? 7 plus 7 minus 14 is 0, right? Okay, so for these three vectors, I have a non-trivial linear relationship, right? I can find a linear combination of these three vectors, so I get 0, a zero vector on this right hand side. And when I form this linear combination, the scalars over here aren't necessarily all equal to 0, right? Okay, so in this case, the vectors are actually dependent, right? You can get one from the others, right? If you want, you could probably take this one over here, and well, you could keep this one over here and move the others onto your right hand side, and you'd get this 1,1,177 in terms of the other two, right? All right. But as I said, that's not really how we. That's a nice way to probably kind of conceptualize it, right? But we sort of work with a more formal definition in this class, right? So the dependence of the vectors is expressed by this sort of linear relationship when you can find non-zero scalars for this, right? Right, and now let's consider the statement over here, right, which is similar to this implication over here, right? In this case, for this vector equation to hold, right, the c's all have to be 0, right? So if you solve this, it turns out that the c's must be 0, right? But in this case over here, if you solve this vector equation, right, the c's do not have to be 0, right? Okay, so this vector equation does not imply that the c's are all 0, right? And if you have that the vector equation does not imply that the c's need to be 0, then these vectors are linearly dependent, right? Okay, so let's look at the definitions from the notes, right? I have a vector space, right? And I have a finite set of vectors in the vector space, right? To start off with, right? Okay, so for example, over here, I have 3 vectors in the vector space R3, right? An equation of this form, right, where you take your vectors over here, and if you can find scalars in C1, C2, Cn, right, such that when you form this linear combination, you get that the right hand side is equal to 0, then this sort of equation over here, this is called a linear relationship, right? Okay, so for example, for these 3 vectors here, right, I can find scalars c1 is equal to 1, c2 is equal to 1, and c3 is equal to minus 1, such that this equation will hold, right? c1u1 plus c2u2 plus c3u3 is equal to the 0 vector, right? Okay, so this over here, this is a linear relationship on the vectors, these 3 vectors here, right? So this is an example of a linear relationship. Right, and in this case, this is a non-trivial linear relationship, right? Anyway, okay, so let me actually show you what a trivial linear relationship is first, right? Okay, so this example here, right, with these 3 vectors, right, what I can do is I can form this linear relationship over here, right? And this linear relationship over here, right, the C1 is equal to 0, the C2 is equal to 0, the C3 is equal to 0, right? So this is of the form C1U1, so this is your C1U1, C2U2, this is your C2U2, and a C3U3, which is this one over here, is equal to a 0 vector, right? Now this is a linear relationship among these 3 vectors here, right? Among the given vectors, and in this case, this linear relationship is a trivial linear relationship, right? It's a trivial linear relationship because all your scalars, the C1, the C2, and C3 are equal to 0, right? So that is what this is saying over here, right? If I have a linear relationship such as this one, right, and if the scalars are all C1, C2, and Cn are all 0, right, then this is called a trivial linear relationship, right? Right. Okay, and going back to this example here, right? If I have these 3 vectors, and in this case I form this linear relationship, notice this linear relationship, the scalars are not all equal to 0, so this is not trivial, right? Or this is a non-trivial linear relationship among your vectors, right? Okay, so let's look at the definition of linear independence, right? I have a vector space. I have a finite number of vectors from my vector space, right? And I want to check to see if they're linearly independent, right? And how do you check to see if they're linearly independent is you consider this equation here, this vector equation, right? Where you have scalars C1, C2, Cn over here. And at this point in time, these are unknown scalars, right? So you consider this vector equation here, right? And with this vector equation, what you do is you solve your vector equation, right? When you solve your vector equation, if it turns out that the scalars C1, C2 to Cn over here, if the only solution to a vector equation is that these scalars have to be 0, then what that means is that the only relationship among the vectors, such as the only relationship among the vectors over here, is the trivial relationship, right? Okay, so for example, if I have these vectors here, these vectors are linearly independent, right? And how you would check to see if they're linearly independent is you can construct this vector equation here, right? Okay, and once you construct this vector equation, what you need to do is you need to solve this vector equation, right? And I think we talked about this very quickly as how you go about solving this, right? And we'll see an example in a second, right? So what you do is you form three equations from this by an equation for each of the components, right? When you solve that system, what will happen over here is that the C1, C2, and C3 must be equal to 0, right? So what that's, okay, so this is your definition of linear independence, right? If when you solve this vector equation, your scalars all have to be equal to 0, right? Then the vectors that you had to start off with, these are linearly independent, right? And well, the fact that these scalars all have to be 0, right? What that is saying is the only possible solution to this vector equation is that the C1 is 0, the C2 is 0, and the C3 is 0, right? Which is this over here. And this is our linear relationship among the vectors. So what this is saying is that this implication is saying that the only linear relationship among the vectors is a trivial one, right? When you have zeros for your scalars over here, right? So that is what this statement is saying here, right? Okay, and then a couple more definitions. So this is a finite set, a finite non-empty set, right? Notice it's indexed with 1, right? And well, what happens if I have the empty set, right? If I have, instead of having this subset with n vectors in it, or 1 or 2 vectors in it, if I have an empty subset over here, well, by definition, that is linearly independent, right? Why you do that, you'll see when we get to basis and so, right? You want things to be consistent, right? Okay, so this over here, this definition is chosen to be consistent with your other cases, right? Okay, but anyway, we just take it as a given for the time being that if I have empty subset, then the empty subset is by definition linearly independent, right? Okay, so the next thing here now is if I have a vector space and I have an infinite subset of my vector space, right? It is possible for an infinite subset of a vector space to be linearly independent, right? So an example is this here, right? Okay, so if I consider a set of polynomials, right? Now this is polynomials, so you could have polynomials of degree 2, you could have polynomials of degree 5, of degree 100, and so on, right? So the scalars for your polynomials here are reals, right? Like the cases that we were looking at before, right? The degree of the polynomial, the highest degree of polynomial could be anything, right? So this is a finite polynomial, but the thing is you have any possible degree of polynomial, right? So you could have a degree 2 polynomial, you could have a degree 1000 polynomial inside this set over here, right? Okay, now this set of polynomials with the usual addition of polynomials and the usual scalar multiplication of polynomials, that's a vector space over R, right? And we saw that, or you would have seen it in the tutorial for in the case of polynomials of degree at most n, right? But it's true for a set of all polynomials when you have no restriction on n. Right. Okay. So this is a vector space over R, right? And if you consider this subset over here, right? So this is a subset with 1 t squared t cubed. And you keep going to t to the n, but this just keeps going, right? So this here is a subset of infinite size, right? It's a subset of your vector space P, because each of these is really just a polynomial, right? Okay, so this t cubed over here, for example, is a polynomial of degree 3, so it's an element of this set, right? And this is a subset of a polynomials P, right? And the size of the set is infinite, right? And this is an example of uh, this is linearly independent, right? So this is a subset of a vector space that is of infinite size and also linearly independent. So how do you check to see if you have an infinite subset over here? How do you check for linear independence, right? Well, you can't really form this sort of vector equation, right, with the infinite amount of terms and examine all the coefficients. That might be it's not impossible, but probably a little difficult, right? So what you do is you consider any finite subset of T, right? So given this over here, what you do is you look at any finite subset and you subject any finite subset to this test over here, right? Okay, so if I look at any finite subset here, right? So for example, if I take t cubed, t to the 15th, and t to the 20, right? That's a finite subset of this infinite subset here, right? And I use the same sort of test, right? Same sort of test for linear independence. So it's t times, so a scalar times the vector, and the vector here is the t, right? Remember, each of your polynomials inside here is regarded as a vector in a vector space. So t is a vector, so c1 times the vector t, c2 times the vector t cubed, right? So, and you have c3 t to the 15 plus c4 t to the 20th, right? And this over here has to be equal to the zero vector, right? Now the zero vector in polynomials is just the zero element, right? Which is just normal zero, right? Okay, and if you have this equation over here, right? If this polynomial is equal to zero, the only way this polynomial is going to be equal to zero is if each of these coefficients are equal to zero, right? Right. So if you have this vector equation over here, this vector equation implies that all your scalars here must be equal to zero, right? So what that means is if I have this infinite subset over here and I consider any finite subset of it, right? You could always subject it to this sort of test here, right? And this sort of test will show you that this finite subset is independent, right? So what I've just shown is that if I have an infinite subset such as T, and so infinite subset T is linearly independent if and only if each finite subset of T is linearly independent, right? And I've given you an argument for that, right? If I have any finite subset of this, it will look basically like this over here. You couldn't go through this process to check to see that this over here is independent, right? So any finite subset of the big T is linearly independent, right? Which means by definition that this infinite subset over here is in fact linearly independent. Okay, so remember this example here, right? I have these three vectors and I want to determine if they're linearly independent, and how I do that is I consider this vector equation over here, right? And I said that this vector equation, right, given this vector equation, if I solve this vector equation, the scalars must all be equal to zero, right? And I suggested or I outlined how you go about solving this vector equation, right? What you do is you multiply this out, multiply c1 times this vector, c2 times this vector, c3 times this vector, add it up, right? And then you just look at the components, right? And what you'd get is you'd get a system of equations. When you solve that system of equations, you would get that the only solution is C1, C2, C3 is equal to zero, right? Okay, so I mentioned that already, right? So let me show you all the details over here in this example, right? So I'm going to do the same thing over here, output for this example, right? Okay, so I have this subset here, right? This is a subset of R3. I want to determine if it's linearly independent or if it's dependent, right? Okay, so the criterion that I use is this criteria over here, right? You're going to form your vector equation, right? So you're going to form this left-hand side, and then you're going to solve this vector equation, and you're going to see if this implication is true, right? Okay, right, so we start with this left-hand side. You start with your vector equation here, right? Right, so the u1 is this 1, 1, 0, and the u2 is minus 1, 2, 0, right? So that's the u1 over here. So the vector equation that we're going to consider is, because I have this vector, I just have two vectors over here. It's going to be c1 u1 plus c2 u2, which is equal to 0, which is this vector equation over here. And now I put in what the u1 and the u2 is, right? The u1 is 1, 1, 0, and the u2 is minus 1, 2, 0, right? Okay, so I have this vector equation over here. Now what I want to do is solve it, right? Now how do I solve it? As I said, what you do is you take your c1 and you multiply it inside over here, right? You take your c2 and you multiply it inside over here, and then what you do is you add them together, right? And for your first component, you have c1 minus c2 is equal to 0. The second component, you have c1 plus, okay, that's an error there. That is 2c2 is equal to 0. Okay. Right, so this should be 2c2 over here, right? So this system over here is c1 plus 2c2 and c1 minus c2, right? But it's not going to affect our solution for us, because when we solve this, what you would get is we're going to get, alright, so you'll get, if you have c1 minus c2 is equal to 0 and c1 plus 2c2 is equal to 0, and you solve that, right? What you'll get is c1 is equal to c2. And when you substitute it into here, what you'll get is 3c1 is equal to 0, and 3c1 is equal to 0 will give you 0. And because the c2 is equal to c1, you would also get 0, right? So this system over here, right, the system where it's 2 over there, right, this will give you that the c's are all equal to 0, right? And once, so the only solution for this system over here is that the c's are 0, right? There are no other solutions, right? You have no non-zero solutions that could satisfy this over here, right? Only this has a unique solution, right? And you can check by other means, and so if you wanted to use an augmented matrix and so on, you could in fact check and see that the system over here would have a unique zero solution, right? So what that means for your vector equation that we have, which is this vector equation, right, is that this vector equation implies that the solutions, the c1 and the c2 must be 0, right? It can't be anything else, right? And if it can't be anything else, then it means that the set over here is linearly independent. Okay. So let's look at our next example over here, where we want to check to see if these vectors, these three vectors over here, if they're independent or if they're dependent. Right, so to check to see if it's independent or dependent, what we do is we use this criteria over here, right? So this is our test over here, right? This vector equation, and when you solve the vector equation, we want to see if the solutions must be 0, right? Okay, so in other words, if we solve the vector equation and we have a unique 0 solution, then it is linearly independent, right? If, however, when you solve this vector equation, right, your solutions are not unique, then it is in fact dependent, right? Okay, so and in fact we saw these vectors already, and we saw that there exists a non-trivial relationship among them, right, which was this relationship. Okay, so these three vectors have a non-trivial linear relationship among them, right? So we expect an answer over here, and we expect the answer that is that this subset over here, it is linearly dependent, right? But let's actually go through the working, right? Okay, so as I said, what we're doing is we're using this criteria over here. So you set up your vector equation. In this case, you have three vectors, u1, u2, and u3. So the vector equation would be c1 u1 plus c2 u2 plus c3 u3 is equal to the 0 vector, right? And now you just put in what your vectors are, u1, u2, u3 over here, and you have your 0 vector on this right hand side, right? Okay, you multiply out, right, and then you add. So for example, C1 plus 2C2 plus 3C3 would give you a first component over here, right? And once you multiply out like this, what you do is you set your left hand side and your right hand, set your component, first component on your left hand side equal to the first component on the right hand side. So you get an equation there, right? Okay, and likewise for the second component, you'll get 7C1 plus 7C2 plus 7C3 is equal to 0, right? And so on for the third component, you get an equation, right? Okay, so these are now equations over here, right? And we know how to solve these, right? You could do this in a variety of ways, right? Let's do it in the way that we did so far, right? What you do is you form your augmented matrix. You want to notice that this is a homogeneous system over here. Your right hand side just zeros here, right? So that means that the system will be consistent, right? And the system is consistent and it either has a unique solution or infinitely many solutions, right? Okay, so yeah, from this system over here, you form your augmented matrix, right? Your coefficients of your augmented matrix. The entries in your augmented matrix are coming from the coefficients here. So for example, this is 177, which gives me the first column here, 177, right? And once I have my augmented matrix, I apply Gauss-Jordan to it, right? And then this Gauss-Jordan gives me a reduced row echelon form matrix that is row equivalent to this one. Okay, and the system associated to this RREF, right? This system over here will have the same solutions as this system over here, right? Okay, so I can get my answer for this system by solving this system here. And how you do this is, well, you express your pivot variables in terms of your free variables, right? Your pivot variables are C1 and C2, right? And so the free variable would be everything else, which is C3, right? And you see that given the form of this matrix, we can always, once this is RREF, we can express the pivots in terms of the frees, right? So you get this. And right. Okay, so the pivots in terms of the frees, right? So let's go back to what we originally had, right? What we originally had was, remember, this, we were considering this vector equation here, right? And from this vector equation, we got the system, right? Okay, so this system, okay, so this system here, right, which is associated to the RREF, it has the same solutions as this equation, right? But okay, so this system here has the same solutions as this system over here. But this system, if you notice, it's really just equivalent to this vector equation, right? Because, well, how do you go from this vector equation to this? What you did is you just multiply everything out and you equate components, right? And you can actually go backwards here, right? What you could do is from this over here, you just consider the components, and then you can separate the components out again and pull out the C1, C2, and C3, right? So the solutions for this vector equation is the same as the solutions for this system, which is the solutions for this system here, right? Okay, so what we have now is that the solutions for my vector equation, right, is given by this here, right? Okay, so for any C3 that I want, right, I can just form the corresponding C1 and C2, and that would give me a solution of my vector equation, right? And in particular, if I use C3 is equal to 1, right, I'd have 1 here, I'd have minus 2 here, and I'd have 1 here, right? Which we saw, right? Which we saw was a solution, right? So if I use C3 is equal to 1, right? C3 is equal to 1 gives me C1 is equal to 1, which is just C1 is equal to 1. Gives me C2 is equal to minus 2, which is just C2 is equal to minus 2. And C3 is equal to 1, which is just 1 over here, right? So we see that when C3 is equal to 1, we get a solution here, right? But that isn't the only solution. You have solutions for any possible value of C3, right? C3 is a free variable. But the point is that for my vector equation over here, the vector equation, right, Okay, and this is just a shorthand notation for the same vector equation. If you consider this vector equation, the solutions do not have to be zero, right? So your solutions for this is not the unique zero solution, right? Solutions for this could potentially include non-zero C1, C2, and C3 as over here 1 minus 2 and 3, right? Okay, so this implication check over here, right? That when you consider your vector equation, right? When you consider your vector equation, this statement isn't true, right? C1, C2 plus C3 equal to 0, right? Does not imply that the C's all have to be 0, right? So this implication is false in this case, right? Which means that your vectors that you had to start off with, which were these vectors here, which were these vectors over here, they are linearly independent. Sorry, they're linearly dependent, right? So they're linearly dependent. Right, so let's recall example that I did in a previous lecture, right? Okay, so I have these two vectors in three-dimensional space. So this is my S. And I want to get the span of these, right? So what's the span of these two vectors, right? Well, the span of these two vectors by taking linear combination of the two vectors, right? And you can take, what you do is you take any linear combination of these two vectors, right? So a linear combination of the two vectors would be of the form C1100 plus C2010, right? And the point about span is you can choose any C1 and C2 that you want, right? And when you choose any C1 and C2 that you want, right? So this is your picture over here. This is the 100. This is the 010. And you take some linear combination of the 100 and the 010. And what that gives you an x vector in the xy plane, right? Okay, and okay, so when you work out this here, what I'll get when I expand it out and collect, right? I'll get C1 in my first position and C2 in my second position, right? So what this means, and we saw this example last time, is that by choosing any C1 and C2, I can get any vector I want in my xy plane, right? Okay, so I can get this vector, right, for some C1 and C2, or if I choose a different C1 and C2, I'll get an x vector, or I can get this vector on the side here, right? Okay, so the set of vectors generated that way by choosing any C1 and C2 that you want, right, is called the span of this S here, right? And the span of S in this case would work out to be the xy plane, right? Because you're seeing that the z is equal to 0, and you can have anything for C1 and C2. So these are all vectors in the xy plane, right? So that in other words, it is your xy plane, right? Okay, and the next thing we want to note is that if I have an S and I take the span of it, right, then the span, if I have a set of vectors S belonging to my vector space, and I take the span is actually a subspace, right? So for this example, my span was the xy plane, and should know by now that the xy plane is a subspace of three-dimensional space, right? It's a plane passing through the origin, so it's going to be a subspace of a three-dimensional space, right? Okay, so these two vectors, when you took the span of them, you got this subspace, which is the xy plane, right? And now the next definition that we want to look at is this definition here, right, which is related, right? So it's saying now that if you have a subspace, right, if I can find some vectors such that when I take the span of them, I get the subspace, right? Okay, so I have some subspace to start off with, right? So suppose I didn't know what the S was over here, right? All I had was the XY plane to start off with, right? So that's an example of the big W, right? Okay, so I have a subspace to start off with, right? And given this subspace, what I want to do is I want to find vectors such that when I take the span of those vectors, I generate my my xy plane, right? Okay, and we just saw that if I use vectors 100 and 010, If I use vectors 1, 0, 0 and 0, 1, 0 and I take the span of them, I get the xy plane, right? So for W being the xy plane, what I want is a span and set, right? So I want some vectors belonging to W, right? So I want vectors such, well, like vectors, a vector here and a vector here, such that when I take the span of these vectors, these two vectors, I get the W, right? And this S over here is referred to as a span and set, right? So it may seem a little confusing given that I'm using this example over here, right? But what you're actually doing is you, in a way, you're working backward, right? You have the subspace to start off with, and what you're trying to do is you're trying to find the vectors that actually will give me the subspace, right? So let's see if we could look at a next example of what a span and set would be, right? So I'm going to go back to my xy plane, right? So the xy plane is this xy plane over here, right? Which is the same as this xy plane, this gray plane down here, right? Right, and so I have my xy plane, and what I want to do is I want to get a span and set for it, right? Now, well, what is a span and set, right? A span and set is if you have any two vectors, well, a span and set is not necessarily two, right? So a span and set is if you have vectors in your subspace, if you take linear combinations of those, right, that would generate your entire subspace, right? Okay, so the example that I just talked about, right, is if I have my xy plane, I can use 1, 0, 0 and 0, 1, 0, right? Because if I take any linear combinations of those, right, I will generate the entire xy plane, right? Okay, so here's a slightly different example, right? So it's the same xy plane, right? Uh, what I have here is the vectors that I have is first vector is 1, 0, 0. So this is 1, 0, 0, which is this one over here, right? That's lying along your x-axis. So the red axis here is your x-axis. And then the second vector I have is 1, 2, 0, right? So this is your vector 1, 2, 0 over here, right? Now what I'm going to do is I'm going to take linear combinations of these two vectors over here, right? So notice my labeling in this. Okay, notice the labeling in the software here, right? This vector 1, 0, 0 is small u, right? The vector 1, 2, 0 is small w, right? And I'm taking linear combinations of the u and the w, right? So the scalars are c1 and c2, right? And the c1 can change and the c2 can change, right? And right, what I want to show is that that will, by changing the c1 and c2 for vectors u and w, right? Notice this w over here is 1, 2, 0, right? So it's not the same as the 0, 1, 0 that I had from before, right? Okay, so taking linear combinations of the u and the w over here will generate my xy plane for me, right? Okay, so all right. Okay, so your the linear combination of the u and the w over here, right? C1 some scalar times u plus C2 some scalar times w, right? And I add those together, right? That's a linear combination of the u and the w, right? And I have this in orange over here, right? Okay, now I program some sliders. In other words, I can choose arbitrary values of C1 and C2 in the software over here, right? So choosing arbitrary C1 and C2, right? What you're seeing is what's happening is that this vector, the linear combination of the u and the w, right, can get you anything in the xy plane, right? Right. Okay, so this linear combination, the C1U plus the C2W, right? This will generate the entire XY plane for once I choose any C1 that I want and any C2 that I want, right? So by varying the C1 and C2, I will generate the entire XY plane. Anyway, so the point that I want to make here is that over here, the vector 1, 0, 0 and the 0, 1, 0, that was a spanning set for my XY plane, right? And I'm saying that over here, the vector, I'm using 1, 0, 0, but I'm no longer using 0, 1, 0. What I'm doing is I'm using 1, 2, 0, right? So your vector 1, 0, 0 and 1, 2, 0, right? These two vectors are now a spanning set, right? Okay, so uh, point I wish to make over here is that the spanning set is not necessarily unique, right? You don't need to use your spanning, you don't need your spanning vectors to be orthogonal to each other. You don't need them to be at 90 degrees. The main thing is that they can't be, at least for the xy plane, they can't be parallel to each other, right? Because if they were parallel to each other, the only thing it would generate is, for example, here, it will just generate a one-dimensional subspace, right? So in order for your spanning set to generate a two-dimensional xy plane over here, they have to be in different directions, right? They need to both lie in the xy plane, but they need to be in different directions. Let's take a look at this example here, where you're given a subset of R3, and the first question here is a little review. You need to show that W is a subspace of R3. Okay, so we saw how to do that already, but we'll do it again. Then we want to sketch W, alright? And finally, we want to find a spanning set for W, right? Okay, so this is our subset of R3, right? What you're saying is that it's a subset where the x is equal to y, right? So y is equal to x, right? Okay, so first of all, we want to show that it's a subspace, right? Okay, so there's three things, or more precisely four things. First of all, you need to justify that it's a subset of R3, and by definition here, it is a subset of R3, right? Because you're choosing vectors that belong to R3 with some condition, but all your vectors are going to belong to R3 in the first place, right? So W is a subset, right? Next thing you need to check is you need to check to see that your vector space is, your subspace is non-empty, right? Okay, so let's go back to our conditions here, right? Okay, so if we want to show that something is a subspace, you want to show it's non-empty, it's closed under vector addition, and it's closed under scalar multiplication, right? Okay, so to show that it's non-empty, you need to just define an element in it, right? And you could consider that the origin 0, 0, 0 is in W, right? Because if you look at 0, 0, it satisfies this condition y is equal to x, right? You see that the y is equal to x over here. So that would mean that this belongs, 0, 0, 0 belongs to W, and therefore W is non-empty, right? Because you have an element in W. Right. Okay, so now we need to check this condition over here that is closed under vector addition, right? So how do you do that, right? Well, what you do is you pick any two elements belonging to W, right? So I pick this x1, y1, z1 belonging to W, and then also this vector over here belonging to W, right? Okay, so, well, what do I know about this vector over here, right? This vector belonging to W means that the x is equal to the y, right? So x1 is equal to y1 here, and the x2 is equal to y2, right? Okay, so what I get is x1 is equal to y1, which is this equality here, and I have x2 is equal to y2, which is this equality over here, right? Okay, and I can add these two, right, which will give me that x1 plus x2 is equal to y1 plus y2, right? And now what I do is I consider the sum of these two vectors over here, right? Okay, so if I have the u and v and w, I need to consider the sum, right? and the sum of these two vectors is x1 plus x2, y1 plus y2, and z1 plus z2, which is this here, right? Okay, so this here is a vector, and now I need to justify that it belongs to W, right? But you see in that from my reasoning up here, right, that y1 plus y2 is equal to x1 plus x2, right? So the y1 plus y2 is equal to x1 plus x2, which means that the y value for this over here is equal to the x value, and that tells you it belongs to W, right? Okay, so I just showed this second condition here, right? And now for the third condition, I pick a vector in W, so I pick a vector in W here. Notice that this vector in W will satisfy this condition that the y is equal to x, right? Okay, so I pick a vector in W. I pick a scalar in R, right? And now, well, I know that the y is equal to x, right? And if the y is equal to x, I can multiply by a scalar to give me that the cy is equal to cx, right? Right. Okay, so I'm going to use this in a second, right? Now, what I do is I consider the scalar multiple of c times this vector, right? And c times this vector x, y, z is cx, cy, cz, right? So I have this here, and I want to justify that it belongs to W, right? Now, well, when is this going to be equal to W? This is going to be equal to W if this y component, which is the cy, is equal to the x component, which is cx over here, right? But we showed that already, right? That cy is equal to cx, right? So the fact that this cy is equal to cx means that it satisfies this condition here, right, for this vector, which tells you that this vector belongs to W, right? So that gives me that the cu belongs to W. Right, so that shows the three conditions, and therefore that the big W is a subspace of R3. Right. Right. Okay. So now what I want to do is I want to sketch this. I want to sketch a subspace which is y is equal to x, right? Right. Okay. So, well, how would I do that, right? It's a subspace of R3, right? And we talked about this already, right? Well, what are your subspaces of R3? Subspaces of R3 are just the origin itself, lines through the origin, planes through the origin, and then R3 itself, right? Okay, so we just need to determine which one this is, right? Is this a point? Is this a line? Is this a plane? Or is this R3 itself, right? Now, okay, so at least we know it's going to be one of those four, right? But we could also use the fact that this is y is equal to x, right? And if we remember the equation of a plane in three-dimensional space, right? An equation of a plane in three-dimensional space is ax plus by plus cz is equal to d, right? And this y is equal to x is actually of this form, right? Where the you can write it where the b is equal to 1, the a is equal to minus 1, the c is equal to 0, and the d is equal to 0, right? So this over here is going to be a plane. Okay, this y is equal to x is of this form, which means that it's going to be a plane in three-dimensional space, right? So we know that it's going to be a plane, right? So now what we need to do is we need to sketch the plane, right? Okay, so how do you sketch the plane? One way to do it is by, say, plotting 3 points, right? You can determine a plane by 3 non-collinear points, right? So what would be 3 non-collinear points, right? What we could do is we could use 0, 0, 0. So this 0, 0, 0 actually satisfy y is equal to x. Yes, it does, right? 0, 0, 0, right? Over here you see in that the y is equal to x over here. So 0, 0, 0 satisfies lies on this plane W, right? Okay, and actually you also justify that it was a subspace already, right? And the subspace must contain the origin here, right? So if you want it, it will come for free, right? That 0, 0, 0 lies on your plane over here, right? Okay, so what would be a next point, right? A next point would be, say, 1, 1, 0, right? If I consider, say, 1, 1, 0 over here, 1, 1, 0 satisfies y is equal to x, right? So y is equal to x would give me this point over here. Y is equal to x. The 1, 1, 0 satisfies y is equal to x, and 1, 1, 0 is this point over here, right? Okay. Right, and what's a third point? Well, a third point is you can use 0, 0, 1, and again that the y is equal to x over here, right? So this d over this point 0, 0, 1 also lies on the on W, right? Okay, so I have 3 points, right? That 0, 0, 0, which is this one here, uh, 1, 1, 0, which is this one here, right? And then 0, 0, 1, which is this one, my z-axis. So those are 3 points on the plane, and those 3 points will determine the plane for you, right? Okay, and if you wanted, you could connect your 3 points by line segments, right? Okay, so what you'd get is you'd get this triangle over here, right? But this triangle isn't the entire plane. This triangle lies on the plane, right? So this is giving you an idea. The triangle alone is face of the triangle is giving you an idea of what the plane is, right? But the plane, what you want to do is you want to keep extending in the direction of the face of the triangle, right? So you keep extend this way, you extend this way, extend this way, extend this way, and that will give you a sketch of the plane, right? Right. Okay, so that would be how you would sketch the plane. You can use 3 points, right? Just construct a triangle passing through those 3 points and then extend out, right? It's a good idea if you say you draw like some lines to indicate what the plane is, right? So for example, what I did, this diagram here, right? I'm not using triangle, I'm using this rectangle over here. So this line I extended out, I extended this line here, right? And then I have these 2 vertical lines here, and then I have this line here parallel to your line y is equal to x. And this over here is good enough to give me a picture of what the plane should look like. So my final question is to find a spanning set for my subspace over here, W, right? Okay, so what I want is some vectors, right, such that when I take the linear combination of them, they will generate the entire plane for me, right? Okay, so I mean, you have a couple ways to do this, right? Um, if you have a good diagram like this, right? What you could do is you really to get a spanning set for W, all you need are just 2 vectors that are not in the same direction, right? So if you notice this vector 1, 1, 0, right, and this vector 0, 0, 1, right? These 2 vectors are not in the same direction, right? And they both vectors in W over here, right? Okay, so these 2 vectors actually will span, right? Any two non-parallel vectors, any 2 vectors that don't lie in the same direction will in fact span the W, right? Uh, and that actually, but I mean, that relies on the fact that you need to know that the W is in fact a plane in the first place, right? And the W, if it's a plane, it's 2-dimensional, so 2 vectors would work, right? So that's more to give you an idea, right? Let me probably give you a systematic way of getting a spanning set, right? Okay, so your systematic way of getting a spanning set would be, what you want to do is you want to solve your equations, right? Okay, so you express, given you would have equations, if you have an equation describing your subspace, right? What you do is you look for solutions of this equation over here, right? Okay, so how many equations do you have? You actually just have one equation, right? So you have equation x is equal to y, right? Okay, so you have equation x is equal to y, and you can write this. We're going to write this in a standard form, right? How we normally write our equations is with everything on the left-hand side and 0 on the right-hand side. So that's what we do over here, right? And we want to go through the same process of forming an augmented matrix and then getting the row reduced matrix, right? And then forming the system associated to that, right? Okay, it's a little unusual over here because you just have a single equation, right? But actually the theory would work here as well, right? Okay, so I have y is equal to x. I can write that as x is equal to minus y is equal to 0. And what I have is I have m is equal to one equation and m is equal to one equation, and this is in three variables, right? This is three-dimensional space, right? Okay, so this is x minus y plus 0z is equal to 0, right? Okay, you have three variables here because you are in three-dimensional space, right? This is notice this is a condition on x, y, and z over here, right? So this equation it's x minus y plus 0z is equal to 0, right? Right. So once you have your equation over here, once you have your equations here, then you form your augmented matrix by looking at the coefficients of this, right? So what are your coefficients? Your coefficients are 1 over here, minus 1 over here, and 0 coefficient for the z, right? And then your right hand side is 0, so you get this over here, right? And because you just have one equation, you're just going to have one row in your augmented matrix, right? Right. Okay, so now that you have this, right, what you want to do is you want to apply a Gauss-Jordan to this, right? But applying a Gauss-Jordan, right, well, you need to check to see if it's in reduced row echelon form, right? You, well, applying a Gauss-Jordan means that you would start with this leftmost entry over here. You would want to make it 1. And then what you'd want to do is you want to make everything else in the column containing 1, 0, right? But there's nothing else there, right? So you can't do anything, right? And then once you finish with this first column, what you'll go to your next row, right? But there's no other rows, right? So because there's no other rows, you'll in fact stop over here, right? So this already, if you apply Gauss-Jordan to this, doesn't do anything because it's already in RRAF form, right? Okay, or you could go through the process of checking to see that your matrix here is RRAF, right? Anyway, so this is RREF over here, right? You have one non-zero row here, right? So let's remember some of the theory that we did. So going back to the theory, well, first thing you'd want to do is, well, you could check to see if the system is consistent using this method over here, right? But you see, you already know that it has solutions, right? If you use 0 for x, 0 for y, and 0 for z, right? Then that would be a solution, right? Okay, so it is consistent already, right? If I mean, this would be a certain amount of work to check to see if it's consistent. Well, let's actually do it, right? So your augmented matrix is this over here. Your pivot is 1 over here, and your pivot is not in this last column over here on this side, right? So because your pivot is not in this last column, you know that from this matrix that your system, your given system, is consistent, right? Okay, so now that you know that your given system is consistent, right, what you do is you could use this theorem to figure out how many free variables I have, right? Okay, so A is the augmented matrix, which is this matrix over here, right? And what you do is from the A, you form the reduced row echelon form by taking Gauss-Jordan, right? But in this particular case, this is already an RREF, right? So the B over here is actually equal to the A, right? If you apply R Gauss-Jordan to get the RREF B, right, that you don't do anything, right? So the RREF over here is just equal to A here, right? Okay, right, so the A is equal to B in this case, and what you look at is the number of non-zero rows, right? So the number of non-zero rows over here in this matrix is 1 over here, right? Right, so you have one non-zero row, right? And the R, so what you are is you in this case here, right? It's a consistent system. We checked that already, right? And you're in this case over here where the R, which is equal to 1, is less than the number of variables. The number of variables, remember, it's three variables here, x, y, and z, right? Okay, so R is equal to 1, N is equal to 3, right? So your system has one pivot variable and N minus R, which is 3 minus 1, so it has two free variables over here, right? Okay, so your solutions can be expressed in terms of two free variables, right? So, well, what's your pivot variable, right? Your pivot variable is what's associated to this one over here, which is x, right? Okay, so your pivot variable is x, and everything else is a free variable. So your pivot variable is x, and your other variables are free, right? Right, so the y and the z are free variables, right? And what you can do now is you can express your pivot variable in terms of your free variable, right? Okay, so by using your equation over here associated to the RRAF, which is just this equation over here, right? You see that this pivot variable you can write in terms of a free variable, right? Okay, so yeah, x is equal, yeah, pivot variable x is written in terms of a free variable here, which is y, right? Okay, so what are your solutions, right? Well, the x is equal to y, right? The y is free, so it's just equal to itself, right? And the z is free, so it's just equal to itself. So the solutions for your system over here, x minus y is equal to 0, can be written in this form, y, z, right? So this one comes from the x is equal to y, and this one comes from the y is free, and this one comes from the z is free, right? Okay, so your solutions are of this form, y, z, right? Where the y and the z are free, right? And what you want to do is you want to notice that I can factor out the y and the z over here, right? And or if you notice that if you expand this out and you add them up, right? What you'll get is the y, z, right? So notice this form over here, right? This y times this vector plus z times this vector over here, right? Writing the vector over here in row vector form, right? If it's less confusing, you could think of this as being column vectors, right? Doesn't hurt, right? You just need to re-express everything here in terms of column vectors. Right, okay, so now that I have this over here, right, what you want to do is you want to realize that this y is arbitrary and this z is arbitrary, right? So what this is this is a linear combination of the two vectors 1, 1, 0 and 0, 1, 0, right? Okay, so the notation for this is that what you're doing is, okay, so this is a linear combination of 1, 1, 0 and 0, 1, 0, right? But you're free to choose any y and z that you want, right? And that actually is, when you're free to choose any y and z that you want, when you're free to choose any y and z that you want, right? What you're doing is you actually take and span, right? Okay, so here you have vectors here, and you're free to choose any C1 and C2 that you want, right? Okay, so what you're doing is you take and span, right? So here I'm taking span of the vectors 1, 1, 0 and 0, 0, 1, right? And the span of those vectors is, okay, so these points over here, right? If you take all possible linear combinations of them, right? What these are giving you is these are giving you all the vectors that belong to W, right? Okay, so in other words, these vectors over here, when you take the span of them, they generate the W here, right? Okay, so, and that is what I mean, that is an example of a span and set, right? Okay. If I can find, if I have a subspace, right, which is this plane over here, right? And if I can find vectors, right, such as this 1, 1, 0 and this 0, 1, 0, such that when I take the span of them, right, when I take all linear combinations of the vectors there, if I end up with my subspace, then these vectors inside here are a spanning set, right? Okay, so the 1, 1, 0 and the 0, 1, 0 are spanning set for W, right? And this would be how you would systematically get a spanning set, right? What you do is for your your subspace over here, you would form a system of equations, right? And from the system of equations, you get the solution set, right? And by factoring appropriately, you can figure out what these vectors are here, right? And these vectors would form your spanning set, right? So let me illustrate through the software that these two vectors here, the 1, 1, 0 and the 0, 1, 0 would be a spanning set, right? For the plane y is equal to x, right? For the subspace. Right, okay, so I have my vector 1, 1, 0, so the vector 1, 1, 0 is this vector over here, and that's this black vector, alright? That's lying on my xy plane, right? And then I have 0, 0, 1, which is this vector 0, 0, 1 over here, right? Okay, so I'm calling the vector 1, 1, 0 in the software, I'm calling it u, right? And the vector 0, 0, 1 over here, I'm calling it w, right? So that's the vertical one here, right? And what I'm doing is I'm going to take linear combinations of those, right? So I'm taking linear combinations of this u over here and this w over here, right? Which is the same as this is the u, so in notation of the software, this is the u, this is the w. Going to take linear combinations of those, so arbitrary scalar times u plus arbitrary scalar times w, right? That's a linear combination of u and w. And with these sliders here, I can change the values of the C1 and C2, right? And let's see what happens when I change the C1 and C2, right? So when I change the C1 and C2, what that is doing is that's sweeping out all the vectors in my plane y is equal to x, right? Okay, so what this orange vector is, this linear combination of the u and w. And by changing the sliders here, right, I'm getting different values of C1 and C2. And you see, for the different values of C1 and C2, I'm able to pick up the entire plane, right?